Presentation on the building of a supercomputer. This is about the building of a supercomputer. I purposely called it the building of a supercomputer rather than the design of a supercomputer because too often as engineers we create wonderful designs that turn out to be unbuildable. Let's face it, it's fun to be innovative, to be inspired and be creative. However, when the fun is completed, the 99% perspiration, as Ben Franklin puts it, needs to be accomplished before we can say we have a product. Now, this presentation is only one half of the 1% of inspiration. It is not a complete design. Rather, it is a method of which a buildable supercomputer could be designed. In the past, the architect would come up with a wonderful design. And the architect would take that design and pass it down to the logic designer. And that logic designer would have to make that architectural design fit into some Boolean equations. Okay, when the logic designer was all finished with that, then he would pass it down to the chip designer. And the chip designer would have to take those Boolean equations and try to make them fit onto a chip. Well, when the chip designer was finished, he would then take those chip designs and pass them down to a board designer, and the board designer then would have to try to make them fit onto the board. And after all this was accomplished, the board designer would pass all of that down to the packaging designer, and the packaging person would try to have to make the cooling fit, the power fit, the connectors fit, and the wire mat fit into a frame. Now this worked in the past because we had low density chips relative to today. We had comparably low density boards, so they kind of all matched these low density connectors. Today, however, our architecture is, you're seeing they have larger memories, more CPUs, larger bandwidth to memories. And there's some exciting things happening in the logic chip design. There's thousands of gates increase in the same amount of real estate. Chips are using more power, however, we're getting more clever with the development of power supplies. They're hotter, but we're getting clever with the way we cool these things. There's exciting things happening in board design. We have multi-layer boards approaching mega-layer boards. We got buried and blind vias, which actually open up channels to board designers that weren't available before. We have interposers sitting on top of boards, which is using IC technology. We have fine line resist, which is allowing us even to put more lines in the same amount of real estate. And there's exciting things happening in the packaging and the cooling. For example, you got floor inert supercooling. In the power, we're getting more and more compact, high output power supplies, bus bars with very capacitance, power converters versus MG sets. And then we get to connectors. And over the past decade, not too many exciting things are happening in connectors relative to what's happening with the rest of the components in a supercomputer. Yeah, there are some zero insertion force connectors maybe at 50 mil centers. And you may see some high insertion force 25 mil center type connectors. But basically we're lagging the other technologies. In the wire mat, the wire is still the very best way to move an electron. However, they're bulky, they're difficult to repair, they're difficult to automate. There's a long assembly time associated with wire mats. And that too is also lagging these other technologies. This statement is very important. Wire mats and connectors cannot be ignored, for they are now the bottleneck of supercomputer packaging. What I'm going to propose are some design steps, and these design steps is what we're all going to be going through together. All of our mixed disciplines will be going through these design steps together. And they're as follows. The first thing we need to do is understand the architecture of the machine, no matter what area we are in. The second thing is determine the maximum determine the maximum allowable time a bit can remain on a wire. Now what this gives us is it actually tells us how tight we can package our machine. Then we're going to start calculating the total wires and determine their interaction with machine elements. Now a machine element in our case is going to be the brick. The interaction between a brick and a brick is wire. Where do these elements need to be located from a packaging standpoint? Then we're going to form a bubble concept of the machine, and from that bubble concept we're going to perform a nodal analysis, and we'll be getting into what a nodal analysis is. From the nodal analysis we're going to go into 1-dimension, 2-dimension, and 3-dimension wire maps. Then we're going to design our first draft model. We're going to design or select the appropriate connectors, and then finally we begin the engineering process of building the machine. And with this, the suggestion will be that this design process is done in parallel and not after the logic designers start designing their logic. Let's start by trying to understand the architecture of the machine. And I will be talking, just in case this isn't coming out on the video, I will be just saying what section and page we're on periodically so that you all can know about where you are. We should all be on section 1. Now some of the information I'm going to present here, because I have tried to become basic in all areas, might be a little boring to some of you when I'm talking about your specific area. But remember, what I'm trying to do is a general education of all areas so that we can all understand and sympathize with each other's problems. So bear with me, because if you're bored in one section, you may not be in the other section, and you may appreciate the level that we're taking the other sections at. So let's start out with some really basics. A supercomputer consists of the CPU, memory, and I/O. A CPU performs arithmetic operations. Memory will store the numbers of the words, and the I/O communicates with the outside world, be it to the operator, another computer, disk drives, etc. Now, the central processing unit, the CPU, needs to write data to memory, and it needs to retrieve data from memory. It performs arithmetic operations on it and stores it back in the memory. Those are the paths that we're going to be going through. And the CPU can also output to the outside world. If we gave a computer a problem, and it didn't have that path to the outside world, then we can never get the answer out of it. We're going to be tracking 3 things. We're going to track data, address, and control. If you think of data as a number or an instruction, and we're going to be calling that a word in a little bit. The address is where are we going to store it in memory, or where are we going to retrieve it. Control is the hall monitor. It's the one that's saying when, where, and how I'm going to do all these things. Keep those 3 basic things in mind throughout this lecture. Those are the 3 things we're going to be tracking. All right, let's talk about an SSI word, or an SS1 word. An SS1 word is 72 bits long. Now you can think of that as a word that has 72 letters in it, except that those letters consist of ones and zeros. Depending on the patterns of ones and zeros I have in that word is telling me what that word says. Now the CPU can only understand the ones and the zeros. It can only understand the 72-bit word. Now, if the CPU needs to talk to memory, and it can only talk in 72-bit words, I'm going to need a path from the CPU to memory where I can write this word, and I'm just talking about one word. Okay, I also need a path from memory to the CPU so I can read words. And remember, control and address. The address is telling me where to go get that word in memory, and the control is telling me how and when. And that takes 46 bits. Every bit is a wire. Every time I have a bit, I have a wire. The only way to transfer a bit to memory is over a wire. So if I have to transfer one word from the CPU to memory, I need 72 wires. And that's where we're going to start. The first wire is to get one bit from the CPU over to memory. We're going to start with one wire. By the end of this lecture, we'll be up to 88,700 wires. And then we will have gone through the basic architecture of the machine. So by tracing the wires, we can start to understand the actual architecture of the machine. Now, are there any questions on write, read, and address? It's a very important concept to have as we go through this. Everyone understand it? All right. I just want to talk a little bit about the basics of supercomputing. If we are to talk about supercomputing and what makes supercomputing fast, it's because we send our words everywhere. Okay? And this is going to become more apparent as we go through the lecture. But essentially, if I have to send a word and it's going over 72 wires to memory, okay, I need 72 wires now just to do that. If I want to read a word back, to make it fast, I put in another set of 72 wires, correct? And what makes that fast means that I can read and I can write at the same time. It's a two-way street. If I have a bridge, and it's only a one-lane bridge, the car's got to wait on the other side while the other car is going across, right? If I have a two-lane bridge, I can now transfer data back and forth. You're going to see this multiply over and over again on what makes computers fast. And I'll try to be giving you, as we go, I'll tell you specific areas of essentially Seymour Cray coming up with the basics of supercomputing on writing data everywhere and then reading it if you need it and write it over if you don't. Okay, and as we go through this, I'll bring you up on that. Okay, let's just digress a little bit from the simple block diagram we have, which is just CPU talking to memory. And this is the block diagram we're going to build on. And let's talk a little bit about clock. Now, every time the clock ticks in a supercomputer, we open and close latches. And we're going to go through latches and differential amplifiers and all this in a little bit. Every tick of the clock, you've got to imagine that I'm transferring a word down a pipeline, for example. The faster the clock ticks, the faster I can move the word. The SS1's clock is 2.5 nanoseconds. So every 2.5 nanoseconds, I'm opening and closing latches, and you can imagine the word traveling down, or a car traveling down a road, but you only get to look at it every 2.5 nanoseconds. It's going to be a little further down its path. And that 2.5 nanoseconds is actually broken up into time segments, and this lecture is not going to cover time segments. In about a month, we'll be doing another lecture which goes more into the internals and shifts and how they're laid out on boards and what's happening on the VTV. But for now, we're worried about machine elements, about bricks. Now, remember I talked about the only alphabet in this word is a 1 and a 0. Okay, the SS1 needs to know what a 1 is. A 1 to the SS1 is when it sees a voltage level of a negative 0.8 volts. And a 0 is when it sees a voltage level of a negative 1.8 volts. Now a 1 is considered a high, and a 0 is considered a low, the high voltage and the low voltage. Now don't get confused just because it's negative. The negative or you can just think of it as that this is a smaller number, but actually it's more positive than the bigger negative number. So just so that doesn't confuse you. We also are going to talk about the inverted signal. All right? And that is the mirror image of what I'm sending. Right? If I'm sending a 1, along with it I'll send a 0. And when we talk about differential amplifiers here, you're going to understand why we do that. Okay? And the clock is what gates the data down its path. Every time I have a tick of the clock, I end up moving my data down the path. All right, let's talk real quick about differential amplifiers. A differential amplifier is a logical gate. You can think of it that way. I want to set an input at a certain state, be it a 1 or a 0, and I want to get an output of a certain state. You get a 1 or a 0. The differential amplifier that I have shown here has been simplified for illustration. I've left off a couple of resistors. In your book, I think you'll see that it says 1.3 volts, and the correct number is negative 1.42 volts to make it look more like an SS1. And it doesn't much matter as we're going through this. However, if you want to make that correction, go ahead. All right, here's how a differential amplifier works. This square wave, and you can see that the square wave is not a square wave by the time it gets here. But for now, let's just take the ideal input of a square wave. Let's say that at point 1 here, we receive a negative 0.8 volts. What that is going to do, it's going to turn on this transistor. Now you can just think of that as a valve. I just turn that valve on. When I turn on this valve, what's going to happen is I'm going to get current to flow across this resistor 1, through my valve, and down through this constant current source. Now, from your basic electricity class, if I have current flowing through a resistor, I'm going to get a voltage drop. So if I take a voltmeter and I were to measure across this resistor, I'm going to have a higher voltage on this side than I will on this side of the resistor. So essentially what I'm going to see is if I put a high voltage in here, I'm going to end up with a low voltage coming out of here because I dropped some of the voltage across the resistor. Now, it's a very simplified explanation of this. Now, let's say that the voltage that I received here is at a lower potential than what I'm forcing this voltage to be. Okay, if the voltage coming in here is less than the minus 1.42 volts, then I'll turn on this valve. And essentially what will happen is my current is now going to flow through this resistor, and if I take a reading across here, I'm going to see a voltage drop at this point. Now what does that actually do? If I put a high voltage here, I'm going to get a high voltage out at A, and I'm going to get a low voltage at A0. If I put a 1 here, high voltage, I will get a 1 at A, high voltage, and I will get a 0 at A0. That will give a low voltage. If I switch it, and I put a 0 here, I will get a 1 at A, and I'll get a 0 at A and a 1 at A0. Okay, and that's essentially what these words say here. And there's a little logic graph here that you can kind of run through the gauge. Now remember, I said this is the ideal situation, but the ideal situation doesn't occur. Because remember that this 1, if I have to move it down a wire, what's going to happen is that square wave is going to degrade and do the losses of inside the wire, and I'm going to end up coming out of the other end of the wire with something that's not too pretty looking square wave. And if you can think about this, if the square wave degrades enough that I'm coming out here with a negative 1.8 volts, and by the time I get over here I'm at a negative 1.3 volts, and I started here from my high at a negative 0.8 volts, and by the time I got out it was 1 volt, and these numbers are a little different in your book, because I think you got the old revs. All right, what happens if I get a glitch on that line? I'm going to draw down my high voltage, and And now what I end up is, let's say that that glitch just happens to be pretty close to the 1.3 volts. Okay, which is pretty close to the 1.42 volts. And I'm putting 1.3, 1.4 volts on this side, 1.3, 1.4 volts on this side. That differential amplifier does not know what it's getting. It cannot differentiate between the 1 and the 0. Because we have losses on the line, now that differential amplifier cannot say whether or not I gave it a 1 or a 0. And that's because this voltage is fixed. So how do you think we're going to fix that? We'll go to the next slide. We're going to fix that by coming up. And by the way, that differential amplifier is how that works on the chips. They set voltages in the chips. You can't do that on a wire, because by the time you get down the wire, we've got so many losses, it can't tell, it doesn't make the difference, it can't see the difference between its reference voltage and the voltage we're feeding. So what do you do to fix that? You say, aha, I'm going to put a high in on this side, and the same time that I put a high in on this side, I'm going to feed the other side of it with the low. Now you can see from that slide, a couple of slides back, of why I had to make a copy. I had to make the mirror image of the signal. Why I have to run a differential pair, right? It's a pair now. So if I'm sending 1 bit, and 1 bit is equivalent to 1 wire, I'm going to have to send a mirror image of it. I better not send it over the same wire at the same time, right? Because it'll just cancel. So I got to add another wire. I send the upright or the high signal over 1 wire, and I send the inverted or the low signal over the other wire. I receive the high on one side, I receive the low on the other side, and now I can differentiate between the high and the low, and this gate works the same. If this one's a high and this one's a low, my A will be a high, my A naught will be a low. I can differentiate between the two. That is the reason for running, it's one of the reasons for running differential signals. But what did it do? It just doubled our amount of wires. Okay, and Kev, let's slide this up just a little bit. There's another thing too, which is neat. Remember that little glitch from the first slide? Well, if you take this and you make a copy of the inverted signal, the glitch is going to show up like that. You add these two together, what happened to the glitch? So there's another advantage of sending differential signals. So, when all of us packaging engineers, and we get real cute, we say, well, Gene, you know, why don't you guys double the amount of signals and run differential pair? Let's just run 1 wire. Well, we can't do that. We could if our wires were maybe an inch long. So I think I'd rather run 2 wires that are 33 inches long than have the restriction. Yeah, you can run 1 wire, but it's only going to be an inch long. Okay? So that's why we're running differential pair, one of the reasons. Okay? So, let's get back to the block diagram. What does that do to our block diagram? Remember what we had? We had 72 bits of write data. We had 72 bits of read data. We had 46 bits of control and address. Well, we got to multiply all that by 2, so we're up to 380 wires. So we're getting closer to 88,700. Okay? Any questions on this? Pretty easy, isn't it? All right, let's look at the brick. And in your book that's labeled the CPU correct, but that's okay. It's really a brick. A little typo here. Now, some of you know, I mean, most of you in this room know what a brick is, but some of the people that will be watching the video don't, so just bear with me here a while. A brick consists of some horizontal boards, some vertical boards, some more horizontal boards, and a wire mat. Okay, and what I show here is on our main boards. I'm showing 4 CPUs, and the CPUs are going to have some sort of a Z-axis communication, and that Z-axis communication among each CPU and among the horizontal boards here is going to happen on the vertical transformation board. Now, the neat thing about using this vertical transformation board is I can take signals off of this board here I can go onto this board, drop down, slide over, and get onto my minis if I want. So that's the purpose of the vertical transformation board. The mini boards here you're going to see are going to be used for some control, some arbitration, and then also it holds the connector that goes to the wire mat. And the other end of this wire mat is memory. Okay, and there's buffer boards and some other things, but for the block diagram that we have so far, if you can just envision memory on the other end of this wire mat, and the memory brick looks the same. It's got some horizontal boards, it's got a vertical board, and then it has some fan-out modules, and we'll be going through what fan-out is and everything else. The basic architecture of a brick for the SS1 is 4 CPUs. Does this need to be split up? No? Okay. 4 CPUs, 2 arbitration nodes, 1 VPD, and 4 minis. And that's shown there. We're going to go through each one of those pieces. All right, let's go back to the block diagram. I talked about arbitration nodes. Right? I also showed you 4 CPUs. And up to now, we've only talked about 1 CPU talking to this pool of memory. Well, in a brick, we've got 4 CPUs, right? And I sure don't want to be sharing this street over the memory, right? Because I got 4 CPUs. It'd really be nice if all 4 CPUs could go out and talk to memory at the same time. So what you think in your mind is, well, okay, what they did was they 4 times the number of signals, or of wires going to memory. Well, they didn't do that. They were nice to us. The logic designers were nice to us. They said, well, we're only going to give you 2 streets over to memory, and the 4 CPUs are going to have to share them. And that's what the arbitration nodes do. The arbitration nodes is a traffic cop that looks at what CPU goes when. And it's just mom sitting there, okay, come on kids, share, okay, it's your turn to use the ropes, over you go. All right, and that's what's happening. But what did we just do? We again doubled our amount of wires. So the arbitration node, there's 2 arbitration nodes, 4 CPUs on a brick. And the arbitration nodes are merely the traffic cops. Who can use the road when? And this is simplified for illustration. I put that note on there. But so now we've got 2 paths going over of 380 wires each. Okay, let's keep building this. All right, SS1, the 428 model. How they came up with the 428 is we have 2 to the 4th processors in the 4th there, which is giving us 16 processors in the 428. 2 to the 28 words of memory, which gives us 268 million. And you might want to make that correction. Words within our memory. Now, that's words. That's 72 bits. Okay, so if you want to get how many bits we have in our memory, multiply by 72, one of those bytes, divided by 8 and all that. But we always talk in words, so you have 268 million words of memory. Now, we also took memory, and from up to now, I've just been talking about memory sitting out here, okay, like this pool. What they have done is they have divided memory up into 4 sections. Right? And then they said, I want all my CPUs to be able to talk to all sections of memory, which means more wires, doesn't it? So now, I just don't have a CPU talking to one little pool of memory. I have a CPU talking to 4 sections of memory. I've chopped memory up into 4 sections. And what did I say about supercomputing? Is you make copies and send it everywhere, and if you're not going to use it, you don't use it. If you use it, you gate it in. Next clock period, the stuff you didn't use gets gated over, or written over. So what do you think happened? Well, now I've got to multiply my number of wires by 4, okay, because I've got to send copies to all sections. Whether or not it gets, is used, it was going to be told on the address and the control. All right? So essentially what that does is it takes our 380 wires and it multiplies it times 8. Remember, we got 2 arbitration nodes times 4 sections, okay, which is actually going to give us 8 paths to memory. And there's 380 wires on every single path. So right now we're up to 3,040 wires. We're getting closer. All right? All right, now, remember when the logic guys were nice to us and they said, well, we're going to let 4 CPUs share 2 arbitration nodes? Okay, well, this slide almost looks like it's contradictory, but then they say, but the 2 arbitration nodes are going to have 2 ports to memory. So that's like, instead of going down Main Street, I'm going to go down I-94. Okay, I got a double lane highway, I can send down twice as many cars. All right, that's what the 2 ports is to memory. And then some of you are going to say, well, gee, as long as I'm ending up with 4 CPUs, right, but then I had 2 arbitration nodes, okay, but then they said there's 2 ports to memory, well, why in the hell not get rid of the arbitration nodes, right, and just take all the ports and stick them right on my CPU boards, and now every CPU, I don't have to do any arbitration, right? See that? Well, the answer is that this is a 428. When we go to a 529, we have 8 sections of memory. So what you do is you take each one of these ports, and now they go off to 8 sections of memory. You see? So we don't have to build 2 different machines. If you want a 428, that's cool. You just got 2 ports of memory. If you want twice as much memory, well, okay, I'm going to put this other memory box over here. I'm going to take this street and reroute this street over to get there. You see, I don't have to mess with anything happening over here on the CPU side. Okay, so at first glance, it looks illogical. But then as you dig deeper into the problem, what it allows us to do is have various machines. Customer can't afford a 529, but he might be able to, in a couple years. That's neat. We're all set up. Same brick in the same place. Same brick works in a 428, works in a 529. Okay, but who paid the price? Us guys doing the packaging, right? But that's okay. Just so we understand why. All right? So let's take a look at how many lines we're going across here. Now remember what we have here is we got 300, every time I draw a line here, I got 380 wires in that line. So I got 380 wires times 2 ports. Okay, that brings me up to the 760. And if you count all these up, there's going to be 8 of those double, lane I-94 interstate highways there. And our wire count now is up to 6,080. All right, I want to just modify or kind of zoom in to just one section of the wire mat. I want to define what I'm calling a node. Now there's a logical node, but this is more like a wire mat node. If you remember, we had a CPU brick here, right? And there was 4 CPUs, and they went through the arbitration nodes, right? We came across here with, in your books, that should be 380 wires. There's a typo there. And if I'm looking at only going to one section, okay, I'll take the other 3 sections and just kind of put them into the background and just zoom in on just one section. There are 3 bricks in one section. 3 bricks make up one section of memory. Okay, if we've got 4 sections, that gives us 12 bricks in our memory in a 428. Okay? And double that for a 529. A node looks for patterns. A node is like your spinal column, where I can take all these wires and I can squeeze them all together into a nice bundle, and then I can branch out from there. Okay, that's what I'm defining as a node. Now that's very important, because what we need to do is conserve on real estate as often as we can, pack things tighter. And that particular node that we have found right here, and you're going to see a whole bunch of these nodes when we get into the interaction matrix, that particular node consists of 1,520 wires. And if we divide by 3, we're going to end up with 507 wires in each one of these sections. And I want you to just keep that in the back of your mind so that you can start seeing patterns start to develop. Okay, and that's the whole idea behind this design, is the patterns that we're going to be forming. Okay, and right now we're far enough along in the architectural design, or in this lecture, that hey, we're up to 6,000 wires. That's quite a few wires, and you already would be trying to look for some patterns, and there is one of the patterns right there. All right. A little bit of a review. We have 72 bits of write data. That's from the CPU to memory. 72 bits of read data. 46 bits of control and address. That gives us 190 bits. And that's a snapshot of just one word. How do we do that? We said, oh, geez, we need differential pairs, and we all know why now, right? So we can drive our differential amplifiers, and after I go through all kinds of losses going over the wire, I can put in a 1 and a 0, the inverted signal, right, to the differential amplifier, and my differential amplifier can now make the difference, or can tell the difference between a 1 and a 0. That doubled our wires, 380, just right there. In a brick, we had 4 CPUs. However, we said we don't want to have 4 paths of memory, 1 for each CPU. We only want 2. So we put in some arbitration nodes, and we said, well, let's put in 2 arbitration nodes. The arbitration nodes are telling which CPU can use the road at what time, right? The path to memory. Okay, and then we said, well, gee, this is too easy for you packaging guys. Let's put in 2 ports. All right? So you throw in 2 ports, and now we've got an interstate, right? You've got 2-lane highway going there, each memory. And the reason we did it at first glance, it doesn't make sense, but the reason we did it is so we could upgrade our memory and split our interstate highway in half and have, again, little county roads running off to 2 sections of memory. So we're going to double our memory in the 529. That allows us to use the same brick. Okay? Remember that all CPUs communicate to all sections. Okay, that gives us a real big bandwidth. We just dump words up to memory. That's very important. That's what makes supercomputers fast. Is that we send everything everywhere. And we're only going to use it in one very small place. But what it eliminates is a whole bunch of communication. And this is actually the way computers used to be designed. Was CPU says, hey, I got an answer. Then had to go ask someone, is the road free? Yeah, the road's free. Okay, can I send my data over the road? Yeah, let me check with memory first. Hey, memory, you got anything coming my way? No, I don't. Okay, the road's free on my way. All right, I'm going to send the word. And then you wait. Memory says, I got the word. I'm going to put it in storage now. You see, and you had the CPU and memory talking back and forth and back and forth. What is that doing? Every tick of the clock, right? I'm wasting time. So how did you make a supercomputer fast? You just sent it there. If you want to, take it. If you don't, hey, leave it alone. I'll give you another one in a little bit, So, and that's all there is to it. Okay.
Yeah. What, putting in 2 ports with your hard nodes, does that mean basically you have 4 paths of memory? Does that mean that each one, all the CPUs can talk at the same time? Is that right?
No, because what they need to do is go through the arbitration node anyway. And the reason for that is because when that machine grows up and becomes a 529, all right, so we can use the same brick. So they still pass it through the arbitration node and then out to memory. Okay, now, it very likely could be, yeah, that CPU 0, both its words went down that path at the same time, but it was still controlled by the arbitration node, not the CPU, right? All right. Well, the logic guys started to feel a little sorry for us, and they said, I want to start cutting down the number of wires in this machine. And really, we went back to them and said, hey, you guys are pin bound. We can't have a connector that has this many pinouts on it. So they actually had to start getting clever. And now you're going to start hearing, there's a buzzword that goes around called bit slicing, right? And you all heard that. Oh, geez, we bit sliced it or across pre-branch. And you all go, what the heck are you talking about bit slicing? This is a real simple concept. Remember the word is 72 bits long? Well, if I took those 72 bits and broke it up into 3 parts, I just did a bit slice. So if I just found the word Mississippi and broke it up into 3 parts and then just read the first part, read the second part, read the first, put it all together, I still have my word, right? And what the architecture in this particular machine does is it says, okay, I'm not going to take 72 bits and store it to brick number 1, and then take 72 bits off of this CPU and store it to brick number 2, because remember, all bits have to go everywhere, right? And I'm going to take another 72 bits and store it to brick number 3. See how the wire count's starting to go up? They said, let's bit slice. Let's take 24 bits and send it to brick number 1 and just load that brick up with the first part of the word. Okay. And then let's take 24 bits and send it to brick number 2, and we're going to load that brick up with the middle of the word. Brick number 2 will always have the middle of the word. I know that. Okay. And then I'm going to take and load up the last part of the word in brick number 3. Now we got to assemble all these words back together again. However, what that does is it saves wires. Okay, we became pin-bound. Pin-bound means that the logic guys wanted to send more out the back than they had holes to send it. Kind of like logic constipation, right? So, that's essentially what's happening when we're talking about bit slice. It's that simple. I'm going to take a word, I'm going to divide it into 3 parts. I'm going to look at the first half, the middle half, and the end half. And when the CPU wants it, I'm going to put it back together somehow. Okay? So for now, let's just keep it that simple. And we'll talk a little bit about address. Now, we should be on section 1, page 14. All right, now. Address and control, if you remember, I said consisted of 46 bits. Okay, I'm giving you that as a definition. When we get into the next series of lectures, we're going to talk about, what each of those bits do on the address and things like that. But for right now, let's just say that that's a given. It takes 46 bits to get 72 bits across the road. Okay. Now that 46-bit is not 100% accurate, because essentially what happens is to save wires, again, we chopped up the address into 3 parts also. And here's how that works. We come across with, let me go through the numbers here real quick. And this is why this is not accurate for illustration, but the 46 bits, if you divide it by 3, comes out to a fraction of a bit. Okay, and that's a little hard. Okay, although some of the real dirty paths might look like a fraction of a bit, there's really no such thing. But I took the numbers off out of here just in case there's some double E's in the audience and you wanted to get real accurate. Okay, so we ended up with, if you divide it by 3, we end up with 15 1/3 bits. Multiply it by 2 for what? The differential pair. And we all know why we need that, right? Because we're going across wire, and the wire is lossy. Multiply it times 2 for the arbitration node. And we know what that's doing, right? It's sharing the 4 CPUs. Multiply it by 2 for the ports to memory, and you know what that does. That allows us to have different models. We come up with 122.667, and if you don't mind, let's just call that 123. Okay? Now, brick number 1 will receive 123 bits for the address, or 123 wires go over there. So it's going to receive about 1/3 of the address. Okay? The brick number 2 is going to receive 1/3 of the address, and brick number 3 is going to receive 1/3 of the address. And then they all share. Isn't it nice? Brick number 1 makes 2 copies of its third, and it says, hey, brick number 2, here's what I got. Boom, boom. And it sends those copies off to the other 2 bricks. At the same identical time, the other 2 bricks are doing the same thing. They're making copies of their part, and they're sending it back to each other. Okay, so they're kind of cooperating back and forth. Now, we really don't need to do this with the data, right? We only need to do this with the address. Because remember, the address is kind of telling us where to go get this part of the word. And the CPU doesn't care where I go get this word, it just wants the whole word, right? So if I say, geez, give me word 15, right? So I send out the address 15, right? Well, let me say 152, so I can kind of make that. I want a word out of mailbox 152. Brick number 1 had the 1, okay? Brick number 2 had the 5, brick number 3 has a 2. Okay, I'm really simplifying this, okay? All right, so then what happens is I need to know on every single brick what the address is so that I can go and get the first half of the word, the first part of the word, the middle part of the word, and the end part of the word, okay? So right when I first receive my address in the brick, I'm going to wait. I'm not going to go get the word yet because I really don't have the rest of the address and I don't know where to go get it, right? All of a sudden, the next tick of the clock, or the next couple ticks of the clock, I don't know how many time periods are between this, but let's just say for illustration, the next tick of the clock, I received my other 2 copies from the guy below me, right? All right, now, and it came up with 152, all right? So I go out to that address and I pick up my first part of the word, all right? And I send it over. At the same identical time, the middle part of the word, because remember the brick below, everybody's sharing, you got the address, middle part of the word, grabs it, sends it over, grabs it, sends it over, automatically assemble these things. And now the only thing I needed to do was fan out 46 bits of address, essentially, and it comes out 123 because all the stuff we have to do. But essentially, I'm fanning out 46 bits of address to all these bricks instead of 72 bits. Okay, so you save wires. And it may not seem like a lot when you look at 72 versus 46, but remember, we're only at about 3,000 wires and we have, 88,700 to go. So, 85,000 to go. Are you understanding this? Okay, so we're fanning the address out once it gets to memory so that, and that's done on those mini boards. Okay, mini board actually does that fan out. All right. Any questions?
What is the copying feature incorporated?
Say again?
What is the feature of copying?
Oh, right in the mini boards. Yep. See that each brick gets its third of the address, let's say. Okay, and it receives it on the mini board. Okay. And then what happens? You're going to see this come out in the wire mat. It's called a one-dimensional wire mat. And what happens is it receives its copy on the mini board and it makes 2 copies. It saves its half, right? Okay, and then it sends those 2 copies down to the other 2 bricks. At the same time I'm sending those, and also I'm receiving. Kind of like one of those trades you used to make as a kid. Okay, I got my hand on your card, you got your hand on my knife, okay, let's go. And you trade it real fast. So it's all at the same time. Okay. And now we got the full address sitting there. So, okay, let's keep expanding this block diagram because now what I need to do is, we've got a pretty good understanding now what's happening with the first 2 blocks. Remember on our little basic computer is the CPU talking to memory. We've got an idea how that really works. Okay, I got a CPU. I can go and get a word. I can bring it into myself, and I can do some multiplications on it or whatever I want to do to it. Or once I have an answer, I know how to send it back to memory. Okay, but remember, the operator out there, or storage devices, or whatever you want to needs it, and we need to get it to the outside world now, right? So we can do all kinds of stuff real fast within the machine. Now we got to fuel it off to the outside world, and that's going to be our input-output, our I/O. Now this, essentially what we're doing here is, I'm going to be using serial number 150. Okay, and by the time we get out 150 supercomputers, I'll be long gone to Alaska, but let's just pretend. We have 150, or Freudian slip. Serial number 150. Now, it can talk to a maintenance computer. Okay, didn't get sick. We got to talk to it somehow, right? All right. It can talk to an IOC, which we call our I/O concentrator. Okay, now the I/O concentrator is a separate cabinet, and what it does is it links up to other things in the world we need to talk to, storage devices, consoles, things like that. Other computers. If I want to hook up to another SS1, now this is called clustering. That buzzword you hear, clustering, oh geez, I can cluster these supercomputers. Okay? That's clustering, the ability of an SS1 to talk to another SS1, and that's pretty valuable. Okay? It gives you some tremendous power, except it takes a long time relative to having memory resident right next to that CPU. Okay, I can grab it right away. And you're going to see why. You're going to see why it takes so long for one SS1 to talk to another SS1. Now, in relative terms to the rest of the world, I mean, this is done in a flash, right? But I mean, relative to what's happening inside one SS1 versus the other, it takes a little bit of time to transfer one word. And we're going to go through a complete word transfer of how one SS1 talks to another SS1 and using buffer boards. All right.
Dan, what are your abbreviations mean? LSS, PDB, PDC?
Oh, I was afraid someone was going to ask that. All right. The P stands for buffer boards. Same reaction I had when someone told me that. Okay. PCC, okay, is cluster to cluster. So it's the buffer boards cluster to cluster. Okay. And the PBB is essentially I/O concentrator buffer board. So they got the BB right on there. So, but all their buffer boards, they started with P. Okay. The LSS, I don't know what that stands for, but it's actually the channel out to the maintenance computer. Okay. What is it? Does anyone know in here? Level scan.
Logic scan software.
Level scan. So we could make up something cool. Okay. Yeah, not on TV.
Level sensor scan?
Level set. Oh, right. Who had that, Dean? Oh, you're on great for a technician, yeah.
Hey Dan, P actually stands for port.
Port. Geez, then that also you guys came up with the P?
No, I just heard it somewhere.
Oh, okay.
PGB is the port global
Port.
buffer.
Yeah, Port Global Buffer. Okay. You use these things so long, you know what they do, but you don't know what they stand for, though. But, all right, let's continue expanding our block diagram and talk a little bit about buffer boards. There's three types of buffer boards in the SS1. The PVBs, the PCCs, and the LSS. And I kind of just said there what they stand, or what they do, not what they mean, or what they stand for. Buffer boards, essentially what happens is I've got, let's say I want to talk to another SS1. Now the SS1, even if it's on a 2.5 nanosecond clock, it may not be synchronized. Okay, I mean this is James Bond type stuff, right? Okay, synchronize our watches. Okay, SS1 over here, serial number 151, is just flying away, and it's going at 2.5 nanoseconds. And the serial 150 is over here, also going at 2.5 nanoseconds, but they don't match. Their heartbeats aren't matching, right? So if I just threw a word over to it, it wouldn't know what the hell to do with it, right? Because I could be out of sync with it. I wouldn't be able to capture it on my latches. What a buffer board does is it grabs data, holds it, syncs it up, and sends it off. Now it actually takes two sets of buffer boards here to do that, one in serial 150 and one in 151. And we'll be going through that here a step at a time. We also need some control to do that, right? Remember this control guy, this overhead that we're carrying around, it's telling me how and when and all that kind of stuff to do things. So we have two bricks in the system. One is called the NRCA, and that's for communication with the CPUs. And RCA, I know, stands for Remote Control Adapter. Yeah, Remote Control Adapter. And the MRCA, which is our Memory Remote Control Adapter. Remote Cluster Adapter. Remote Cluster Adapter? That's right. Okay, thanks. All right. Remote Cluster Adapter, thanks. All right, let's go through a one-word transfer. Essentially, here's how we hook up an SS1 to another SS1. We're going to be doing that through buffer boards, and we'll step through this one step at a time. Okay, so right now we should be on section 1, and just turn to page 18. Okay, here's what happens. One of the CPUs in serial 151 says, hey, I'm requesting a word from serial 150. Now it's going to go off and it's going to request that word through the NRCA brick. Now, the reason I'm mentioning some of these bricks here is because when we finally get to the organization and the nodes, is when they were designing the NRCA brick, they ran out of logic, so they had to share MRCA got some room left over, essentially. So part of the NRCA sits over on the MRCA, so you're going to see some weird wires. But essentially, this is just a cleaned up version of that. Okay, the NRCA then transfers that request to the PCCs and it locks it up into its buffers and gets it timed so that when that request is sent over to the buffers over here, that I'm at latch time with the 150, with serial number 150. Okay. Now it's able to send it to its MRCA, okay, which then goes out and fetches the word from memory. Okay, so now that word is sitting on the MRCA. And as you turn your page, we'll keep going. The MRCA captures the word out of serial 150's memory, passes it again to its PCCs, passes it across the boundary to serial 151's PCCs. It once again goes into the NRCA, and the NRCA gives it to its CPU. That was the transfer of one word. Now that's a little different than CPU saying gimme and it gets it. Okay? But it still does give us some very powerful computing power by being able to hook one supercomputer up to another. Any questions on that? That's just kind of a block diagram of it. All right. Well, if you go to section 1-20, this is where we are so far. It's starting to look a little busier. Okay. And now what we have done there is you can see the 3 bricks in a section. That's right in here. 3 bricks in a section. You can see what that's doing here. That's that address span out. All right. You can see our wire mat node. And our 2 ports, that's the heavy line here, from our 2 arbitration nodes from a CPU brick. Okay. You all kind of have a gut feel of how this is working. It's pretty simple. It's just keeping track of a whole bunch of little simple things. The hardest thing with this whole computer is remembering what all the letters stand for. All right. Now, if I want to talk just, oh yeah, we can go to the next slide. All right, and this here is a blow-up of, if we take a look at one CPU brick. You can see our CPUs, they're being shared arbitration nodes, okay? And if you see there, it's actually, you never see a line drawn from a CPU over to memory, do you? It's always the arbitration node going over to memory, okay? And the arbitration nodes, those are the heavy lines going over the memory, and that's quite a substantial amount of wires, all right? Then you have arbitration nodes, again, going out to maintenance computer, right? PVDs, which is actually the same buffer boards, but they're going out to the I/O concentrator. And again, the same type of buffer boards, we're trying to sync up data. Out to the MRCAs, and we went to a really simplified version of transferring one word. And the NRCAs. Okay. So that's basically where we are in our block diagram. I don't have an overhead of this next one, but Dale Smith came up with a really neat block diagram that's on your next page. Oh, I'm sorry, the next page after that, 1-23. And he's in the process, too, of modifying that and trying to make it simplified and things like that. But that's giving you basically the system and some of the crossbar things that we're going to be talking about in the next lecture. All right, I think this is going to be a good place for a break. And when we come back, what we're going to be talking about is how long can a bit stay on a wire. And we're going to start getting into allowable time a bit can remain on a wire. Section 2, page 1. All right, you're going to have a few, just a note to add on the bottom of your page. On the old Rev, your pages don't have this note on the bottom. You might want to add those in as well. If I were going to talk about a latch, and I was talking about the clock period before, and every time the clock ticks, I open and close the latch. Essentially what happens is I've got just X amount of time where I can send data, the latch is open, and be able to grab it when it closes. All right, so if I have a baseball in this hand, I'm going to send it over here. I've got to coordinate that so I can catch that baseball, say, right at the same time that the latch closes. Now, if, for example, my latch-to-latch time is so fast that 2.5 nanoseconds is the case, that my wire would have to be so short, okay, by the time that those latches are opening and closing, my wire length is going to be too short to actually build a machine. So what you end up doing is storing a bit on the wire. So we're going to talk about a 1 clock period wire, a 2 clock period wire, and a 3 clock period wire. And for purposes of illustration, I'm just going to say that a 1 clock period wire is 10 inches long, a 2 clock period wire is 20 inches long, and a 3 clock period wire is 30 inches long. Now in real life, and that's what the note is on the bottom of your page, is a 1 clock period wire is less than 1 inch long. Now, there's no way we could package all those CPUs and all those, wires within 1 inch of each other. That means that if I had a CPU brick and I have all these other memory bricks, I could only have 1 inch of wire. All right. Now for illustration, I'm going to say that's 10 inches. But the reason in real life it's only 1 inch is because it takes time for me to open those latches and to close those latches. All right. So in one tick of the clock, it's going to take me some time to throw this data, and it's going to take me time to open up, and it's going to take me time to grab that. All right? Now, in 2.5 nanoseconds, sure, I can throw an electron across the 10-inch wire about 9 something. Let's just say in 2.5 nanoseconds, I can have an electron travel with a 10-inch wire. But because I'm using up the time in the latch to throw and catch, that wire now shrinks up to only 1 inch. All right? Now, what happens on a 2 clock period wire being 20 inches long is that at latch time, I'll have one of the bits at this latch, one of the bits at the other latch, but it's 2 clock periods long, and we end up with 1 bit being stored in the middle of the wire at latch time. Now that's scary. We're actually using the wire as a storage device. That bit, that letter of the word, is not latched anywhere. It is stored physically on that wire. Now that means that we have to really control the quality of our wire, because we're actually going to use it as a storage device. So let's just take a look at that just a little bit further. All right, I show on page 2, section 2, I show latches at the end of both ends of the transmission line. I've got a very sloppy clock going in to both latches. Right, remember, the latch is going to, the clock is going to set off that latch. Now, ideally, these latches open and close at the same time. And ideally they receive that clock pulse at exactly the same time. But in real life, that's not the case, because our clocks move just a little bit, all right? And we can't clock everything exactly at the same time. Okay, and that's called clock skew. It's the tolerance of the clock. All right, ideally those latches are going to open and close exactly at the same time. But that's not really true. There's a certain delay to take it open and a certain time to close it, and not every one of them are exactly the same. So they have a tolerance associated with them. Okay? And ideally, the bit will travel along all 90,000 some wires all at the same time. And that doesn't make much sense, right? Because not every single one of those wires are the exact length. They're going to have the exact same one on top or the exact thickness. So there's some skew associated with that, some tolerance in the wire. All right, we got a latch delay. That's to how long it takes to open, how long it takes to close. We got all these tolerances and all these skews. And if you add those all together, they need to be less than or equal to the clock period. Otherwise, I'm going to end up missing my data. I got a different way of explaining that on the next page.
That,
Yes?
so that equation with T max equals
Mm-hmm. Where am I at?
1.
Yeah, less than or equal to.
No, the line before less than or equal to, you have T max plus T clock skew.
Oh, yeah.
T max equals.
Equals, right, I'm sorry. That's another typo. Tmax equals, right, clock speed. Thanks. Brad, you got that one too, right? Okay, good. All right, let's take a look at this and let's just talk about this more in mechanical terms. All right, here I show 4 gates, and all these gates you can imagine are synced up and they're all swinging at the same time. All right? And I'm going to launch a little steely marble across the plane. All right? Now, the ideal situation is that I can launch this marble and these gates are all turning at the same time and it rolls across this surface and it gets hit by the second gate just right at that nice time, right when it's coming around, and it goes again and again and again and again, right? But in real life that doesn't happen, right? The coefficient of friction, for example, may change between here and here, all right? It may be faster, it may be slower. If I get there too early, what's going to happen? That ball is going to pass right through that gate. I'll never get to hit it. If I get there too late, the gate's already swung around, and the ball's going to bounce off of it. Same thing with these latches. If I send a 1 across these transmission lines, and it gets there too early, you know, it's like one of the little kids, you know, you throw the ball and it hits, hits the chest and he misses it, right? So you're going to time this kid sitting there going like this, right? With these latches, right? If it gets there too late, it bounces off his head and you miss your data. That's the same thing that's happening with these latches. So when the electrical people come to us and they say, oh, geez, you got to be able to cut your wire length to plus or minus 10 1,000ths of an inch or whatever, you know, you got to kind of listen to them, you know, and they say, well, geez, that's not possible, but I can cut it to within 1 millimeter. Okay, and that's what the argument is back and forth that they're talking about. Is they have electrical tolerances the same as we have mechanical tolerances. Right? Now, if you take section 2, page 4, in the books you have, I use the word wire. After we discussed it for a little while, I changed that to path so that it's not confusing, because what I'm talking about here is the entire path from latch to latch. Now, that includes some time in the silicon and it includes some time on some flex circuit and things like that. So this slide shows the correction, and I don't think the corrections are in the books yet. All right, well, let's just say, for example, now, then you look at me and you say, okay, well, that's really neat. If I have a long enough wire, I wouldn't really even need any memory, would I? I could just store everything on a wire and make it through 30,000 miles long, and eventually it's going to come back. And so let's just take out this memory section. You know, I mean, that's a little bit of an exaggeration, but essentially, we mechanical people would sure like to have as much wire as we possibly can, right, in order to spread this machine out. Well, something happens on this wire. You have to remember that these latches are gated by a clock. They're opening and closing and opening and closing by a clock. But when a bit is on a wire, there's no clock there. There's no latch there. There is nothing controlling the physics of that bit moving down the wire, right? It is going to travel at 98% the speed of light down that wire no matter what. No matter if my gates are a little slow or if my gates are a little fast. The wire, the bit knows how fast it wants to travel down the wire. We don't have any control of that. Okay, so let's see if I were to take and say, I can tolerate 10% of my path between that latch, one latch to the next latch. Well, if I have a short wire, 10 inches, okay, it'd be like plus or minus 1 inch for a short path, plus or minus 1 inch, right? But look what happens when I get up to like 40 inches, and I have 10%. Now that's plus or minus 4 inches. Now remember what's happening is these latches are opening and closing at the very same time, okay? The bits are traveling down the wire at a constant, and I'm not latching them. But now all of a sudden, I've got 4 extra inches that I have to go down the wire, right? The bit doesn't know that. It's not going to get there. It's going to get there too late, isn't it? Because I'm on the other end of my tolerance, 4 inches. All right? Or if I was short, like 36 inches, it's going to get there too early. So what we need to do is we have to determine what is the skew window electrically. And in our machine, I think it's fairly obvious that a 1 clock period path is too tight. I'm talking about the wire mat. Now, we got all kinds of 1 clock period paths on the silicon and the quartz. And in the wire mat, it's too tight. A 2 clock period path is within our restraints, within our packaging restraints. We have to get real clever with our packaging. However, we've already released a whole bunch of RITs, and it would cause an entire RIT release. The entire machine would have to be redesigned to implement this plan. Okay? A 3 clock period path is right on the border. It's yellow line. We're not going to be able to margin our machine very much. Okay, we can't change our clock speed. So remember, if I have 2.5 nanosecond clock, and let's say that we plug in the wall and the machine doesn't run. Now typically what you do is you try slowing the machine down. Well, geez, it didn't run at 2.5 nanoseconds. Let's try running it at 3 nanoseconds. What did I do? Every 3 nanoseconds, the latches are now going to open and close, right? But did I stretch my wire? No. So those bits are still thinking it's traveling down the wire at 2.5 nanoseconds, right? The time it would take for a 2.5 nanosecond clock. So you see, what I can't do is slow the machine down without physically getting in there and say, oh, geez, today we're going to run at 3 nanoseconds. Hey, Dean, come on over here and stretch these wires, okay? Because that's essentially what it'd have to take. So we lose our clock margin the longer these wires get, okay? Now, if there was a little short 1-inch path, yeah, okay. 10% of that, of a 1-inch path, a tenth of an inch, yeah, we might be able to deal with that. 10% of a 40-inch path, you know, now we're way beyond the skew. The machine is broke for the 4 clock period path. You would never know if the bits are getting there or not. So this becomes one of our packaging constraints, is that we need to know that, yeah, we can build a machine in a 2 clock period path or a 3 clock period path. That's our restraint. Okay? Now we actually know how long that wire needs to be, and it's about 30 inches. Okay. Now when we start writing ground rules and things like that, we have to know exactly what that wire needs to be. Deepak.
You have a note on one of your earlier slides which said, in reality, due to latch delay, a 1 clock period wire is less than 1 inch long.
Yes.
But you said between 2 and 3 clock period wire, it's talking about 2 and 3 inch wires.
Oh, no, because here's the neat thing about that, is because you only count the latch delay once, because there's no latches on the wire. See? The latch delay is only once. Open, close. All right? 1 clock period path, open, close. 2 clock period path, open, close. But there is no latch delay on the wires. So I'm just 98% speed like right down that wire. So now I've got a lot more length. So that's why when I'm going 10 inches, 20 inches, 30 inches, it's not really truly correct. But, you know, for illustration, you can see what I'm saying. All right? Okay, let's go into section 3. The remainder of these sections don't take as long as section 1 things, right? Or we'll be here until Christmas. So, section 3, we're going to be calculating the total wires and determining the interaction with the machine elements by creating an interaction matrix. That's a mouthful. I just kind of wrote that in there because, it just kind of sounded important. But essentially what we're going to do is count wires. And we're going to count wires and we're going to figure out where they go. As a matter of fact, we're even going to say that they have to go here even to get the machine to work, in a 2-clock period machine. Remember, the bottleneck is the connectors and the wires. We have gone, we have just taken leaps and bounds with all the photolithography work on ICs and boards and things like that. And physically, we still have that restraint to that wire. Okay, so this whole proposal is based on, let's start with the wire. Once we understand the architecture, we can start with the wire and we can design in the other direction. So it's going to be reversed of what normally has been happening. Now I suppose we'll still have to listen to the architect, right? But at least we can start saying, hey, what's happening with logic design a little bit? Maybe we can get some of these pinouts to come. All right, now, if we go down these calculations again, they're all calculations you've already seen, and you should all feel pretty comfortable with them. Starting at the top of the page, we know now how we got our 190 bits, which was the 72 bits of data in, the 72 bits of data out, that's the read-write data, the 46 bits of control. We multiplied that times the 2 twisted wire pairs, remember, for the differential amplifier. Okay? We again multiplied it by 2 for the 2 ports to memory. Okay? We then had said we had 4 sections in memory, and remembering what makes a supercomputer fast is that we write everything everywhere, whether we use it or not, we send it everywhere. So we have 4 sections of memory. That brings us up to 3,040 pins. And remember, there's 2 arbitration nodes on the brick, right? So you multiply that again by 2, and you end up with 6,080. Now, we also talked about the CPU, and it has to talk to another, or SS1 having to talk to another SS1. All right, if we take a look at some of those numbers, essentially it takes 98 bits for the CPU to talk to the MRCA, and you just kind of read down the line there. It takes 196 pins to do that. All the 2 times twisted is all differential pairs. All right, the CPU talking to the NRCA is 708 pins to do that. 58 pins to talk out to the maintenance computer, that's the LSS. All right, and I should be using this. The PVB is where I'm at right now. CPU talking to buffer boards, the PVB buffer boards is 712, etc., all the way down the line. Now, remember what I'm showing here is I'm really only showing 1 brick of CPUs, right? There's only 1 brick of CPUs shown here. Now, if we were to take and continue to try to do this using block diagrams, knowing that we're going to be ending up with 80-some thousand wires, the block diagrams would get a little messy. So, essentially what I said we need to do is we need to form an interaction matrix. Now, I'm going to tell you how to make an interaction matrix. Interaction matrix is nothing more than like a mileage chart you see on maps. Okay, it's just an easy way to put a whole bunch of data together. It's also a really neat and easy way to look for patterns. And it's going to become real obvious after we've created our interaction matrix. All right, again, we're looking for 88,700 wires. The first step in forming an interaction matrix is we need to define our machine elements. And those machine elements we're going to call bricks. We've got CPU bricks, right? Memory bricks, MRCA bricks, brick, single, NRCA brick, and although they're not in brick form, they're still machine elements. We have LSS, PBB, and PCC buffer type boards. Okay, and communication channel maintenance. Now, it becomes real easy. What we do is we just simply make a list. You make a list on the x-axis of all the bricks, and then you repeat that list on the y-axis. Now, once that's repeated, you'll eliminate the redundancy. And I'll show you that's just merely drawing a 45-degree angle and eliminating the redundancy. After you're finished with that, we just start filling in the numbers. Pure, simple, here are the numbers, you fill them in. how many numbers go between brick 1, section 3, and CPU 5 through 7 or 8. Okay? Once we see that and we've got all our data organized, the nodes should fall out. The nodes, remember what the nodes are, that's the spinal column, places where we can group things together in groups and then fan out from there. So that you don't have to spend time doing it, I did it for you. On the next page is the interaction matrix. You can see that I have listed the 4 CPU bricks, and this is for 428. 4 CPU bricks giving me 16 processors, and the 12 memory bricks, and section 1, brick 1, 2, and 3, because there's 3 bricks in the section. All right? And then I listed some of the oddballs down here, the LSS, PVV, PCC. Now, the way you read the interaction matrix is, what is the interaction, or how many wires are there between memory section 1, brick 1, and CPU 0 through 3? Or did I say 1 through 4? Yeah, 1 through 4. Okay. Well, there happen to be, what, 507? Yeah, 507 wires. Well, gee, look how many 507s we have. That's the pattern. Now remember in the past when all this logic was passed down on top of us, and we put all these boards in a frame, and then what we do is we take these frames and we turn them upside down, and we'd hire a whole bunch of people to gather around them and have this little quilting bee, and everyone would be sitting soldering wires together, and you looked at these wires and it looked like spaghetti, and we'd all brag and we'd say, oh geez, there's 66 miles of wire in our machine. Okay? Well, it never has to be that way. It was only that way because they could get away with it. We can't get away with that anymore. You physically cannot get inside these machines anymore to wire them that way. We cannot have our little quilting bees, humans, putting these wires together. There are physically too many of them in too small of a space. What does that mean? That means we need to look for patterns. We need to break the wire mat up into sections. We need to distribute these sections into different places of assembly, and we need to automate that. And then put it all together into a modular form. Now look at the patterns we have here. I see a pattern in this interaction matrix of 507s. I also see a patterns of 369s. See the patterns with 369s? You know what that is? Remember when we fanned out our address and all the 2 bricks had to talk to each other and trade signals and everything else? Well, there's my pattern of 369. That's the address fan. I mean, you see where understanding the architecture is going to help us to build these machines together? Because we're address fanning out. That happens on every single section. That pattern is there all the way down the line. Our wire mats don't have to look like spaghetti anymore. Okay, etc. You can see there's some 254s in there that are patterned up, and 708s. Now, the neat thing you can do with this is you can add up all the totals. To add up a total, you have to add its horizontal and its vertical column. Oh, I told you I was going to tell you about redundancy. Redundancy is you draw a 45-degree line across here because everything on the upper half of a matrix is redundant. It's just a flip. Okay, so you just draw your 45-degree line. Okay, well, we got some really heavy-duty patterns in here. Now, once we study that, we can now develop some sort of a bubble diagram and start looking for some nodes. All right? So let's go to the next section, forming the bubble diagram. Deepak.
Previous diagram.
Okay? Interaction matrix.
The 190 that you see from the MRCA to the MRCA is that portion of the MRCA that you're utilizing for the MRCA?
Yes, exactly. That 190 is an oddball set of wires because they ran out of the room designing the NRCA. Yep. Because normally from the architecture there wouldn't be any communication. Right. Exactly.
I got a question about it too. The tail end of the 3rd section of each memory section, only talk to the MRCA, doesn't talk to every other memory.
Okay.
So
Say that
how
again.
memory 1.1 and memory 1.2 will talk to
Right,
Memory
there
1,
is-
2, and memory 1, 3, they're moving like serially, so memory 1, 3 always goes out to the MRCA.
Yes. In fact, the section never needs to talk to another section because it already got copied.
Right.
Okay, so you'll never see, that's really a good point, is because wherever you see blanks in here, what does that mean?
Yeah.
Those guys could be 20,000 miles apart because there's no interaction between them. And you see now how we can start taking these bricks, moving them around, so where there's a lot of interaction, they end up being next to each other, and when there's not, there's like big spaces. You just don't take bricks and throw them into a column and say, well, the industrial designer says this looks cool and it's not going to cause our CEs to go mentally retarded because, of the shape or something. Or that we're going to build the shape of this computer based on where the stars are, okay? We got to build the shape of our computer based on our architecture, okay? I mean, I would rather have an ugly machine that works than a pretty machine that doesn't work. You can always throw a plexiglass cover over it, right, and make it look cool. So, all right. So anyway, that's the interaction matrix. Any other questions on that? Okay, let's take a look at the bubble diagram. Now, a bubble diagram is just that. They're bubbles. And the reason I call them a bubble diagram or a balloon diagram is because that's just how it starts out. You have a balloon, and you push here, and it'll bulge here, and you push there, and it bulges there. Pretty soon you start pushing and pushing and putting things in the right place until you don't have any more bulges, and then it ends up being your machine. Now, our bulges here happen to be the numbers of wires, okay? Trying to hook these, move the bricks around. I've gone through that and gone through different possibilities, and this is not the only possibility. However, this is one that works, for example. Now, I'm going to just zoom in on this so we can see some of the wires, which is the next slide. Essentially what happened is our bricks ended up in a hexagon. Now, John Gill came up with a frame design that looks just like this, and the only thing that the interaction matrix drops off is kind of suggests where to put the bricks. Right. Now, you can see also here that we have, I've got to orientate myself with this overhead. Okay. We have 1,521 wires right in this area. Those are the wires that go from this brick column to this section.
Section 0.
Section 0? Right here.
No. Remember that one?
Oh, okay. Yeah, I'm still trying to edit this thing. I have a real bad habit. When I used to do logic design, you start counting at 0. Okay, so I kind of switch back and forth. So if you can kind of, until we get this thing edited better, sometimes I call it section 0 and I start counting at 0, and sometimes at 1. So that's my mistakes throughout here, and people are catching as we go. All right, I have this column of CPUs, and that's CPU 0 through 7. And in the interaction matrix are probably 1 through 8, right? Okay, and it's talking over here to section 0. Now, that tells me that, gee, there's no sense of coming out here and forming all kinds of spaghetti and then come back into here, right? It means I can just put a nice little wire mat right through here. And I've already used 1,521 wires to talk to that section. Well, over here, we have 738 wires, and they kind of look like they're staying just right with that brick. And I've got, when we do a nodal analysis, now this is kind of like the start of a nodal analysis. This is a thinking process, okay, getting your nodes defined. 738 wires are sitting here, and they kind of communicate right in that column. Okay, so kind of make a note of that. All right. And, well, gee, I've got this many wires that need to cross this boundary over here. Okay, to communicate to those other bricks. All right, so from the bubble diagram, you actually start a thinking process. Now, what that thinking process turns into is actually a nodal analysis, which is our section 5 and 6. Before we start the nodal analysis, I want to do some definitions. So right now, you should be on page 5 and 6, page 1. So section 5 and 6, page 1. I kind of merged those two sections together. All right. I want to define a 3D wire mat a 2D wire mat, and a 1D wire mat. Now, a 3D wire mat is a wire mat which crosses the center line of the hexagon, which is parallel to the face in question. Now let me have Kevin put up that last overhead we had. A three-dimensional wire mat. All right. Let's say that this is the brick in question. Is any wire that passes the center line of the hexagon parallel to the face of the brick in question. All right. So if I cross that center line, I'm calling it a 3D wire mat. Now, and these are just definitions I made up, guys. It's not anything official, but just to keep this stuff straight. In other words, if I'm communicating with this brick to any brick that's touching it, it is not a 3D wire mat. If I'm communicating from this brick to any brick that's not touching it, it is a 3D wire mat. Okay? So once I cross this center line of the hexagon, parallel to the brick in question, I'm into a 3D wire mat. The 2D wire mat, the definition of it is any wire mat or any wire that needs to go from one column to the next column. Okay? One column to the next column without crossing the center line. Okay, so the 2D wire mats are all these little jumpers from brick to brick. And a 1D wire mat is defined as a wire mat that stays within the column. Now, if there's 3 bricks in a section, okay, you have 3 bricks in a section, and we know that those 3 bricks are all going to be in a column. What do you think we could put into a 1D wire mat? The address span out, that's right. Because remember what that thing does. It just shares its address with everybody else. It doesn't care about sharing with any of the other sections, right? And it doesn't care about sharing it with the CPU. It has remained within that brick. Okay? So that kind of makes it look like these 738 and 738, there's no interaction between those two, right? They can be standalone 1D wire mats that just drop in. Now you can go off in another room. You can be in another world making these wire mats. They don't need to be sitting around the quilting table, right? We can have, and I know this is going to be like socially retarded, right? But you can have some guy off in his room all by himself making the 1D wire mat. And then drop it in the machine later.
That's assuming you work out your pinouts, right, so that they don't interact when you try to put it together.
Yeah, you're ahead of me. Section 9 comes up with these conclusions, right? Because right now, the pinouts are random. And that is the whole point of this presentation. We cannot afford to be random anymore. We need, as packaging engineers, to dictate where these pinouts are going to come out in the module set. Okay? And that's going to become real clear here. In fact, to you, it's already become real clear. Of course, you knew that from before. All right. Now, let's just take a look at, I think you've got, let's put that dash 6. All right, if you go down here to this part of 5 and 6-1, that's where we start defining what's going to be a 3D wire mat, etc. All right, a CPU column to a memory column. Anytime you have any kind of communication within a 2D wire mat, and let's say that I can run a 1D wire, but I'm also running 2D wires in the same space, the 2D wire mat is going to win out. Okay, now the reason for that is the automation. If let's say I pick one of the corners of the hexagon, I define that that corner is going to be a 2D wire mat. All right? I don't, and I know that I'm going to be crossing over like this, but I can put some 1D wires in that 2D wire mat, okay? It's just that the 2D wire mat wins out. It would be a fold-out thing. And we've got some models to show you that here in just a little bit. All right. I go through some calculations here of how I do the nodal analysis, and I think what I'd rather do is let you read that, and I want to get right into the pictures. And the next page also, 5 and 6-2, we've been through this enough, I think, that y'all know where those numbers come from now. So let's just go right into the nodal analysis and go to 5 and 6, page 3. All right, let's take one brick in question. All right, and that particular brick is going to be CPU brick 0 through 7. Now, in this particular design, we had the MRCA and the NRCA sitting below it. But remember, this is an example of a design. This thing is pretty dynamic right now. All right. Essentially what this is showing is anything with an X in the middle, and I think there's a couple of them missing in here. There's some typos on here. With the X in the middle is saying this is going to be a 1D wire mat. The square is a 2D wire mat, and the triangle is a 3D wire mat. And you can start to see some of the patterns that are forming there. As a matter of fact, if you were to take up and add those wires, essentially what we end up having, and this is real important to remember, because it's going to be hard to understand how to make a 3D wire mat without remembering this. It's about 50% of the wires in this machine are 3D wires. Only 50%, it comes up like 58%, are 3D wires. And that's going to be real important to remember when we start assembling the 3D wire mat. Okay, so there's the nodal analysis which came from the interaction matrix. Now, how to analyze this nodal analysis says, well, gee, I'm going to need one 3D wire mat. Okay? I am going to need 4 2D wire mats, and I'm going to need 4 1D wire mats. That means I have 9 individual wire mats. Now let's take a look at that. Okay, here's 2 wire mats right here. I just took this corner and said I'm going to put 2 1D wire mats here. Okay, here's a 2D wire mat. All right, over here is there should be 2 1D wire mat, a 2D wire mat. And essentially what you say, you add them all up, I have 9 individual wire mats. Because remember, you only got 2 ends for the wire, right? And once it's plugged in, it can't go anywhere else. So if I already put an address fan out, for example, in the 1D format, I can pull that wire mat out, that one can be assembled somewhere else. I can have 9 wire mats being assembled at the same time. All right, and that's what that nodal analysis is showing. All right, let's skip right into section 7, the second nodal analysis for I/O. And again, it's just going through numbers. So section 7 is actually kind of what a model that we can work with. Now, I'm a real firm believer in modeling. I believe that I like this computer modeling. I like computer modeling a lot. However, if you can set a model on your desk and hover around it, there's some real value in it. Now, I understand, that, yeah, I can't set a 747 on my desk, full scale. Okay, but fortunately, we can set a full scale SS1 on our desk. Well, kind of. What's represented over here, and Jeff, can you see this model on the camera? I don't know if you have to zoom in on it or not. But over here is a model of essentially what fell out of the nodal analysis. Now remember, this is a bubble diagram model. It has nothing to do with the frame, it has nothing to do with cooling. It is just merely showing that, hey, if we put the bricks here, in this particular position, we may be able to make our reaches. Okay, and inside that model, we have a wire mat. And we're going to be pulling that out pretty quick. So we start hovering around this model and we start looking for real estate. And trying to come up where we can be putting our connectors and selecting connectors. Okay, so that's our next step, is actually coming up with some sort of a model. All right, I think what I'd like to do here is, before we get into the connectors, there's a little bit of setup we need to do. Essentially, Kevin's going to pull out the 3-dimensional wire mat off of our model and set it on the table. We're going to have a little bit like a Mr. Wizard experiment here. Of appropriate connectors. Now this is the top view. Okay, it's almost the top view. All right, we have the top view of the bubble diagram that we showed you, the model. Okay, the model, top view is a hexagon. Okay, now remember, this is just the bubble diagram of this. Whether or not the frame comes out like this, we don't know. But this is kind of like where the bricks lie. Right now, the model looks like it's going to be about 10 inches on the side of a hexagon. Now, the really neat thing about a hexagon is that a side is equal to its radius. It's actually not the real radius, but it's all 60-degree angles equal out of the triangle. So if I'm 10 inches across here and 10 inches into the middle, I'll be 10 inches into the middle. And just kind of keep that in the back of your mind when you start unfolding a three-dimensional wire mat. And keep in mind also when we start to unfold a three-dimensional wire mat is that a three-dimensional wire mat actually communicates to the bricks that are opposite, crosses the center line that's parallel to the face of the brick in question. Okay, and the 1D wire mat is the ones that are horizontal along its own column, and the 2D wire mats will cross over a column that touches a column. All right? And also remember that a 2 clock period wire, now we just chose 20 inches for this particular demonstration. A 2 clock period wire is about 20 inches long. Now that's, it's less than that, a little less than that, but just for demonstration, we're just going to call it 20 inches. All right, if I were to take, let's turn the page now, we're section 8, page 2. If I were going to take and make a three-dimensional wire mat, three-dimensional wire mat would actually be enclosed inside this hexagonal cylinder. It actually would be enclosed. Now, we could not wire this thing because of the density of wire. You can't reach down inside the cylinder and try to wire things together. So you need to unfold the hexagonal cylinder. What I'm showing here is this hexagon being unfolded into 6 parts. But remember that it was 10 inches, about 10 inches was the side of one of the hexagons. If I unfold this out, and if I have 6 parts and they're all 10 inches each, that gives me something that's 60 inches long. And if you remember, I've got to communicate. All CPUs communicate to all sections, so my worst case distance is going to be the transverse distance across all of those. Well, if I'm already folded out to 60 inches and I'm sitting with a 20-inch wire, there is no way, right, that I can reach all points in that folded out hexagon. Okay, keep that in mind. We'll go to the next. Our connector in this machine on the Mini is about 6 inches long. There's about 4,000 wires that come off of that connector that go into a 3D wire mat. And there's about 2,000 wires per side, okay, going from one column over to the next, going from one column over to the next, per side that go into 1 and 2D wire mats. So if you look at this, about 50% of the wires come out of the middle, and in this design, and about 50% split over 2 sides come out the edges. Okay? If I take, go to the next page, if I say, okay, I only need 50% of the wires that got to go into a 3-dimensional wire mat, and I've got a 6-inch connector, that means I theoretically could take 3 inches out of the middle of that connector. And then I can dedicate that to connections that are going to go into the 3-dimensional wire mat. All right? Keep that in mind. All right, now let's start doing the magic trick. On the next slide, envision pulling those 3-inch sections away from the 10-inch section, laying them down flat on the table, and pushing them together. Now, when I take 3 inches times 6 inches, or 3 inches times 6 sides of the hexagon, I end up with 18 inches. Now, that's a hell of a lot shorter than the 60 inches I had, right? Okay. Now, that's 18 inches and I got a 20-inch wire, right? But I still have to go the diagonal transverse distance, right? Okay, so I'm still a little short, ain't I? Okay? All right, well, let's go to the next slide. Now, envision this hexagon unfolding. When the hexagon unfolds, I unfolded it where a brick intersection met, right? Does a three-dimensional wire mat ever communicate to one column touching the other column? No, it does not. So when I unfold there will never be communication between this column and this column in the three-dimensional wire mat, because that has been taken care of in the two-dimensional wire mat. Okay, so it unfolds, I lay it flat, and if you look now, my worst case distance, this is just transverse diagonal, I'll show you in just a little bit. It's actually 15 inches across, and our column height is about 18, 19 inches. Okay, remember, these are just rough figures. Okay? So my worst case is coming down to about 23.43 inches. I'm getting close to that 20 inches. I'm getting a lot closer than I was with the 60 inches. All right, if you go to the next slide. To get it to 20 inches, what we are going to do is put a slight cup. Now remember what this thing is looking like, and I'm going to show you here in our little Mr. Wizard experiment. But it's laying in a cup. All 3-inch segments are butted together. Now I'm going to kind of fold them up a little bit in a cup until I can make my three-dimensional reach. Now, let's talk automation real quick. If you can envision, I'm going to patch cord this. It's like a telephone operator, right? Patch cording in, one end this way, one end that end. Okay, now, you can envision this segment rolling on an automated machine, okay, and I'm patch cording. Okay, so I'm here once, and then I roll, and I bring up another one, and over the other. All these wires are the same length, aren't they? I load this automated machine, and I start patch cording with this roll. All right, now that machine needs to be designed, but this is the fun part, right? The 0.5% of inspiration. Okay, let's take a look again where our three-dimensional, one-dimensional wire mats came in. And then I will take, we'll do our little Mr. Wizard experiment. From the nodal analysis, and this is the review, I have a two-dimensional wire mat, a two-dimensional wire mat, two one-dimensional wire mats on both sides here, a two-dimensional wire mat and a two-dimensional wire mat and a 3D wire mat in the middle. So there's one three-dimensional wire mat. And remember, I can take each one of these wire mats individually and have them being wired in separate stations. Okay? Plus the 3D, right? So there should be 9, I believe, 9 wire mats there. 1, 2, 3, 4, and 4 is 8, and the 3D one makes 9. Okay? So there's 9 individual wire mats in this machine. Now let's do our little Mr. Wizard experiment. We're going to have to move the camera around. And this is an amateur production anyway, so we're going to look a little chaotic here. All right, we'll focus in on this. I might need to grab hands and stuff here. All right. How you doing there, Jeff? Okay. Yeah. Ready? You got it here? This is a three-dimensional wire mat. Now what I'm going to end up doing is the brick, you can envision a brick sitting here and out from the model. The brick sits out this way at every piece of fiberglass, or plexiglass. What I'm going to do right now is find the place we need to separate it, right here. We're going to separate and take a section out. What I just pulled out of here was a two-dimensional wire mat. This wire mat was wired somewhere else. Okay? And we just set it down. And we continue to do this. Am I doing this right, Kevin? Okay, and I just took out another, this one might have been a one-dimensional wire mat. Actually, it would be two one-dimensional wire mats. Now, we'll have to have fixtures and things to do this, but and again, I'm taking off more one- and two-dimensional wire mats. We didn't bring our curved cup in, did we? This is a challenge. Yeah, I think it's like, okay, Jim. And we're still taking apart 1- and 2-dimensional wire mats. You nervous? I am. Karen should. We got one more to get off. Now what we're going to do is we're going to unroll this at the star. Okay. And lay it down. We don't have our curved section, but this actually sat in a curved section. Now what would happen is our automated machine would just be doing patch cords in here. If we get a break in this wire mat, and we're actually trying to design this wire mat so that we'd have between no more than 2 to 4 breaks throughout the lifetime of the machine, is that all the bricks theoretically could be pulled out a quarter, half an inch, and this wire mat could be slid out. It could either be shipped back to the factory, or the customer engineer on site could open up this wire mat with the proper fixtures, find the wire. It's going to have some sort of a barbed insert, take the wire out, and put in a new one. The 1- and 2-dimensional wire mats also would be patch corded in the same way. All right? And now to assemble it, the opposite would be true. Any questions on that?
How do you get away from the 23.3 inch?
Oh, because now when this curves up, 23.3 inches is when it's flat.
Okay.
Right, and that would be the worst case across here, but now when it curves up, that's why we needed to curve it up.
Oh,
Okay? So, these are about 20-inch wires in here right now. This is all 1X models were made.
So it probably won't lay flat if you try to.
No, in fact, what happens is that the boards slide. The boards slide in this. Okay? Any questions? All right. You know, I think I'll put it back together later when we're not on camera.
Say, Dan?
Yes.
Are these twisted parallel? This is still patch cord?
Yes.
How do they do that?
Well, actually what we're going to have to do is,
Sitting on the, sitting on it, yeah. Okay.
you know, production problem here? Okay. There. The question was asked, are these differential pairs that gets patch corded? Yes, they are. We have not designed the connector yet, but what I'm envisioning is that that end of the connector would actually be a double wire because they're twisted together. Double connector, barbed plastic housing, pushed into a hole. If we go with the present system we're using today, that particular part would actually be a blade, 2 blades, plastic housing with barbs on it. And then we'd need some sort of a tool that the tool would actually close the barbs down, you know, from the back side and then pull it out. So, and again, that's inspiration part of it. Perspiration isn't there yet. Let's take a look at what this actually means. You can go to Section 8, page 9. What does this mean for wiring? Let's use the time required to wire a 428. We have approximately 90,000 wires, let's say, in a 428. And if we talk about a very slow automated process, a very slow automated process would be 2 wires per minute. That is really slow. Okay? Now, that means it would take 1 minute to plug in a twisted wire pair. So this is really a slow automated process. 90,000 wires divided by 2 wires per minute gives me about 45,000 minutes. All right. Now I can divide it by 2 stations, and I'm just using the 2 stations instead of the 9 stations. Okay, and the reason I use 2 stations was because about 50% of the wires are being in the 3D and 50% are in the 1 and 2D. Okay, so either I could wire those really slow, the 1 and 2D ones really slow, or you see, because there's a bottleneck there. Okay, the 3D was the one that takes the longest time. But anyway, let's just divide it by 2 because we have 2 stations. All right, that gives us 22,500 minutes. You divide that by 60 minutes in an hour, gives us 375 hours divided by 40 hours per week, gives us 9.37 weeks divided by 3 shifts. That's 3.1 weeks to wire an entire 428, which now takes us about, what, 6 months, John? About
6 to 8 months.
6 to 8 months to wire. So, now, let's just say that we wanted to go with not a slow system, that we wanted to go with an automated system that might be twice as fast. All right? That puts our wiring time down to a week and a half. To wire an entire 428 from 6 to 8 months down to a week and a half.
Plus the human factor is out.
That's right, yeah, because it's all automated. John just said the human factor is taken out, yes. Any questions? All right, let's talk a little bit about the connector.
One question, we haven't in fact eliminated any wires at this point.
Yes, I do absolutely no data hopping in this machine.
What would data hopping?
Oh, okay. If you package a machine, and let's just say we put bricks into a machine, and we don't take into account the wire length, what happens is pretty soon there's a brick that's further away than the wire we have. So what you do is you go out of, let's say, the CPU module, you come onto a memory module, but it doesn't happen to be the memory module that that bit needs to go to. You latch it up there, and then you come out again, and then hit the brick it's supposed to
2
go.
wires for every wire that's above.
Right, exactly. You just see what you did to your connectors? Okay.
Now, how many wires would you estimate this would eliminate?
This eliminated about, I believe it was 20,000 wires that we eliminated with this design. So it was close to 100,000 wires, and we got it down to about 80. So,
Even if you had to manually assemble this design, you'd still save a lot of
yes.
time. If you didn't
Right. In fact, the first, I'm sure the first 3D wirement we do is probably going to be manual. At least halfway until we can get the machine built. Now, these machines are, I mean, this is not like it needs to be invented. It kind of needs to be invented for this process, but they are out there for insertion machines. Yeah. And they're a lot faster than 1 a minute, believe me. So, yeah.
On your previous slide, you used a 40-hour week. It's an automated process. Why not use a 7-day week?
Well, it was a religious machine. All right,
So you can shorten it by
right, we can go down to 3 days.
40%.
That's right, yeah, 4 days. That's cool. That's substantial, yeah. Okay, so anyway, again, this is inspirational, right? It's not, nothing is in stone here, but I think it kind of shows a bit of a savings. So, all right, let's talk real quick about the connections. Now, the brick is the field replaceable unit. Okay, if something breaks, the brick comes out, it gets sent back to the factory. The factory fixes it. I don't know if they've really decided if a brick is on site or if we are going to buy a jet and I get to fly it, you know. But essentially, somehow they'll have a new brick. Okay, the brick is back here to be assembled. So let's take a look at what connections we have. We have a brick, and there's going to be some sort of a pad. That's that one. There's got to be some sort of connection to that pad. All right. Then we need to separate the brick from the frame. All right. And that's this connection 3 to 4. And there's some sort of a wire mat. Okay. We need to separate the brick on the other side that it's communicating to, right, from the frame. And then we have another connection and a pad here. Okay. So that we can get some sort of connector out here to the frame. Now, the goal is to eliminate as many of these interfaces as possible. That's going to reduce the complexity, and also, what else does it do? It cleans up that signal going over the wire, which the electrical people have been asking us to do forever, correct? You turn the page, I'm proposing a connector design here, and again, inspirational only, of the ideal connector is actually going to be a connector where I have a controlled impedance right to the pad. There's no big blades or forks or barrels or pins or any of that stuff. Essentially, you just take a wire and you put it right to the pad. My shield and everything goes with it, right down to the pad. Now, why not build the perfect connector? If you turn the page, we're doing some experiments on this right now. And the guy running the camera, if he's not successful with them pretty soon, I told him to pick up an application at McDonald's.
You can raise that, Jeff.
Okay. Essentially what we're doing in our experiments is we're drilling two pieces of dielectric. Now that dielectric, the first piece is 25 mils thick about, and the second piece is 5 mils thick. All right. Once those are drilled, and they're drilled as mated sets, and they're drilled at the array pitch of what the pads are on the mini boards, we insert wires, and the wires got insulation on them. You've got some designs not without insulation, but essentially wires are put in through those holes. Now, once the wires are fed through the holes, they get ground off perfectly flat at that 5 mil piece of dielectric at the bottom. Okay. So right here we did a grinding process. Now then those wires get potted, and we pull off 5 mil plate on the bottom, and we do a laser ablation. Now what the laser ablation does is it's going to either strip insulation if we've used insulation, or it might even form a ball on the end. But we're in the middle of those experiments. I'd like to give special thanks to Jeff Janicki, our engineer, Kevin Ostrud, technician, Nona Johnson, technical support, Sandra Wilson, technical support, my wife Diane, mental support, for their long hours and patience in helping make this presentation possible in the allotted time frame. Thank you. Johnson, technical support. Sandra Johnson, technical support. My wife Diane for mental support, for their long hours and patience in helping make this presentation possible in the allotted time frame. Thank you.
You might want to redo that instead.
Routed on the mini, not on the wire mat, in order to make this scheme work. Now, if we look at conclusions, okay, the pin out of the backplane connector needs to be defined prior to the selection of chip position. The wire mat in the 428 is not random. The wire mat needs to be automated. The wire mat needs to be modular. The wire mat needs to be repairable. Connectors need to be chosen so that the most proven part remains in the wire mat. And connectors need to be repairable, which I said twice. Oh, the wire mat needs to be repairable. Okay. All right, you can skip that slide. And last but not least, I would like to thank Jeff Janicki, Kevin